All right, so now that we know that the cross product of two connected spaces is connected, and by induction, the cross product of any finite number of connected spaces is connected, the next natural question to ask is an arbitrary product, or well, maybe not an arbitrary product for next, but the next natural step, maybe the easiest thing to do would be to consider the accountable product of connected spaces. Is that connected? And the answer there is it depends on the topology that you use. It turns out that it's not an arbitrary product, or even a countable product is not connected in the box topology, but it is connected in the product topology. Remember, in the difference between the two is that in the box topology, the box topology has a basis. That is, the basis for the box topology is the product of open sets. Any product of open sets is a basis element for the box topology. For the product topology, a basis element would be a product of open sets where only finitely many of the sets in the product are actually different from all of R. So let's just talk about this and show that in the product topology it is connected. Okay. R omega, and again, because we know that the real numbers are connected. So, so let's what do we do here? Let's start off with okay. So we're going to define a set here. We're going to use that same result. Essentially, we're going to show that the union of a collection of a collection of connected spaces is connected when those connected spaces contain a point in common. So that's been a very useful result so far. So define Rn this way. Rn is going to be the set of all sequences in R omega, okay, such that x sub I equals 0 for I greater than n, right? So a typical element of Rn would be an element that looks like this: x1, x2, up to xn, then followed by all zeros. That is in Rn, okay? And so now basically it's going to follow from the last theorem by this theorem 23.6 that Rn is connected. So it's connected because it's essentially just a finite product. It's just, the Rn is connected, right? So this capital Rn it's basically homeomorphic. Homeomorphic to Rn, right? The real, this is maybe it's an unfortunate name here. Rn is different from, this is R sub n, this is R to the n, right? So it's homeomorphic to this. You can easily define a continuous function from Rn, this Rn, to that Rn by just mapping a sequence to the first n coordinates. That's going to be a invertible map that is continuous, and so and the inverse will be continuous as well. So the continuous image of a connected set is connected. So these are all connected here. Also, note that the sequence of all zeros, right? This is in Rn for every n, right? So that tells us that, so we have a bunch of connected sets that contain one element here. So that tells us that, they contain the same element. So the union then, as n goes from 0 to, not 0, 1 to infinity, okay? As n goes from 1 to infinity of R sub n, that's going to be it's going to be connected. It's connected by that theorem 23.3. Okay, so unfortunately, if we could say that this union is R omega, then we'd be done with it, right? unfortunately, that union is not R omega. So let's just say this. Let's let R, just to simplify notation, let me let R equal the union as n goes from 1 to infinity of R sub n, okay? So it turns out it's that R is not equal to R omega, okay? Because R omega is the set of all sequences, but R is essentially the set of all sequences with all but the first finitely many terms are 0. Okay, so this is, basically if you have the sequence of all ones, for example, that's not going to be in R because it's not in Rn for any n, right? So R is not equal to R omega, but we can show this. But we can show that R closure equals R omega. And since R closure, if R is closed, R closure will be closed. That's by theorem 23.4. So so R omega is closed, or is connected. I said closed, I meant connected. R omega is connected by theorem 23.4, which we proved in a previous video, that if R is connected, the closure is connected, okay? Actually, any set between R and its closure would be connected. So that's all we've got to do. If we can show that the closure of R is equal to R omega, then R omega will be connected. So how do we show that? Well, let's let A be some sequence, right? Let it be some sequence in R omega, right? I mean, R omega, the closure of R is clearly contained in R omega. R omega is the whole thing, right? So we got to show the other way around. Show that any element of R omega is going to be in R closure, okay? So let's, so the way that we do that is we need to show that any neighborhood of A is intersects with R, okay? So let's start with a neighborhood of A. So let's let, and a neighborhood of A is going to look like a product of open sets, basically. Let this product here be a neighborhood of A, okay? So it's a neighborhood of A. So again, keep in mind what that means in the product topology. This is a basis element. More precisely, I'm going to let this be a basis element containing A, because if you can show it that any basis element containing A intersects R, then any open set containing A will intersect R. So let's take a neighborhood, a basis element that contains A. So what that means is that UI equals R for all but finitely many I, right? So for all but finitely many I, U sub I equals R. So so let's figure out what we can say here. All right. So all right. So what we know here, what this basically tells us is, how is that going to relate to these RNs? Remember what these RNs are. These RNs are basically, whoa. These RNs are basically the set of all points where everything after a certain point, all the coordinates after a certain point are 0. So that's going to lend itself really well to working with this neighborhood, because everything after a certain point, since this is U sub I equals R for only all but finitely many I, then eventually for all any element of this set, for all the coordinates after that can just be any real numbers, okay? So let's look here. Let's see, so what I'm trying to say here is that there exists an n such that for if I is greater than n, then that implies that U sub I equals R, okay? All right, so now let's consider this element. consider the element A1, A2, all the way up to A capital N, and then everything with a 0 after that, okay? All righty. So we know here that this element, what am I going to call it? I'm going to call it, I'll call it lowercase r, right? Okay, so r is in this product here. Okay, because it's, you know, it's a neighborhood of A, so the first n coordinates are in the first n coordinates of this, and then so, but then after that, at any point, the coordinates after that are in the reals, right? And so for any element in this set, the coordinates after the nth coordinate are all, can be anything you want. So we just made them to be equal to 0. So r is going to definitely be in this neighborhood here, and it's also in it's in Rn, right? It's in the set of all points whose first and for all of whose coordinates except the first n coordinates are 0. And since R sub n is just a subset of the union, this is going to be the product of the, this is going to be a subset of this here, the union of, as I goes from 1 to infinity of R sub I, right? Okay. Maybe a better way to say this would just, let me just call it, sorry about this. It's getting a little bit messy. It's the, there's R sub n is a subset of R. So this sequence element is an element of this set right here. So any neighborhood of A is going to intersect R. Any neighborhood of A intersects R, right? So that tells us that A is an element of R closure, which is what we wanted. So basically any A in R omega is in R closure. So R closure equals R omega. Okay. So that's a proof that the product topology is connected. The product topology, R omega in the product topology is connected. There's another result here, which I don't think I'm going to prove, but it basically says R omega in the box topology is not connected. It's example 6 on page 151. I would encourage you to read it. It's pretty slick. It's just, you know, that you can find this. They find a separation for R omega in the box topology. They look at the set of all bounded sequences and the set of all unbounded sequences, and those are both open sets that are disjoint, and their union is all of omega. So R omega. So I'll let you read that though, and I'm going to stop the video here before I run out of room.